Welcome to the next video in the Measure Theoretic Probability series. This is video number 7, and we'll be introducing algebras. I hope this will be a short one. I'm just going to define an algebra, say just a little bit about intuitions, and we'll do some more interesting stuff in the next video. But an algebra is basically defined by a bundle of properties that are things we just sort of want a collection of measurables to have. I don't know why we call it an algebra, by the way, just as a matter of nomenclature. There is something slightly algebraic in its feeling, I suppose, but I couldn't argue it any better than that. Anyway, so let this calligraphic A be any subset of the power set of omega. And notice already that that is somewhat like a collection of measurables, right? A collection of measurables is always going to be a subset of the power set of omega, as we said earlier when discussing the canonical examples and the vocabulary associated with that. But we say that that collection A is an algebra. If it contains the universe, that means omega, the universe, the universal set, is an element of A. And it must also be closed under complement. So if E is some element of A, then its complement is also an element of A. And it must also be closed under pairwise unions, meaning that if you take some two subsets of omega, call them D and E, and they are in the algebra, well then, to be closed under pairwise union, their union must also be in A. And so any subset of the power set of omega satisfying these three properties is an algebra. Now, I briefly just want to talk about why is an algebra defined in this way. And so, why do we require that any collection of measurables be closed under unions? Well, I take this one to be the most intuitively compelling of the properties, because if you can measure a subset A and you can measure a subset B, then you ought to be able to measure their union. That just sort of feels intuitive. Certainly, if you think about it in the case of intervals, right? Seems like if you can measure one interval and another interval, then you ought to be able to measure their union. And we know that we need that for the theory of Lebesgue integration, right? Not just is it a feeling, but it certainly also something that we more or less must have in order to make good on the Lebesgue integration project. But also when you're not thinking just about Lebesgue integration, but these more general measures and more general integration, again, it's, you take the example of counting measure, probability measure, or direct measure, or just about anything that seems like a measure, seems like it ought to have this property. Now, what about closure under complements? Well, this one's a little bit harder, I think, to give a strong intuition for. But I would suggest that, well, for one thing, it just doesn't hurt. If you think about length measure, if you take any interval, which we know we want to be able to measure, let's think about a bounded interval, like, for instance, the interval from 4 to 7. Well, its complement is essentially these two disjoint, you could call them rays, right? Because they start at a point and go off to infinity. So, it's this union of these two, call them interval rays, if you like. But in any case, whatever. The point is that we have a pretty obvious thing that we're going to say the measure of this thing is. It's infinity, right? It goes off to infinity. So when thinking about length measure, that should have measure infinity. So that kind of shows you that because we can assign it measure infinity, that there's really no problem in having this among our measurable subsets. That doesn't really say why we require it, though. It just says why it causes no harm to have it. And I think the best argument that I can make for why we require this to be in an algebra is because you will find that as we go through proving various facts about Lebesgue measure, length measure in particular, and general measures as well, we will be using this property. It'll show up as something that really we either need or at least find very useful in giving proofs of some other facts. And so it causes no harm, and it allows us to perform important proofs of other facts. So it seems valuable. And I can't really convince you that it makes proofs easier or even possible until you actually see those proofs, which, we will be getting to, but can't do it right now until we build up some of the intermediate material that's necessary. So I think all I can really say is look out for yourself, right? As we go through the future material, look for the right. If this concern is interesting to you, then just keep your eyes peeled, notice when it comes up, and wonder, well, if we didn't have this requirement, how much of the theory of measurement and integration would suffer, because we can't prove this theorem, or at least it would be much harder to prove some given theorem. And I think all of the same is just as true for the requirement that an algebra contain the universe. Again, it causes no harm. We can assign a measure to the universe in every example that we can think of. It seems somewhat intuitively correct, more or less. And it's very useful in proofs. And so look out for that as well in future proofs.